Welcome back, everybody. This is lecture 27 on intermolecular forces. Mr. Johnson with you. Happy New Year. It is the year 2021, and it's going to be a great year. So we're on page 391 of our ebook or 383 of our textbook. And I'd just like to recreate the storyline so far for you about what we've learned up until now, at least as it pertains to intermolecular forces. We know that when nonmetals form bonds with relatively similar electronegativities, they do so by sharing electrons to form covalent bonds. Two or more nonmetals that form bonds create molecules, molecular solids with distinct molecules. We know that Lewis structures can help us predict what the geometry of those molecules will be. If you draw a Lewis structure, you can determine whether or not those bonds are polar. And if that molecule is asymmetrical and it has polar bonds, we know that that molecule is polar. Meanwhile, if a molecule either has nonpolar bonds or has polar bonds but is symmetrical, it is nonpolar. The reason why we've learned that skill, learning about geometry and polarity, is to be able to predict what type of intermolecular forces exist between those molecules and how strong they are, so that we can predict how they'll behave in nature, what their boiling points might be relative to each other, what their melting points might be, how soluble in water they might be. So that's what that storyline's all about. The first thing we want to do is be clear about what intermolecular forces are and how they're different from intramolecular forces. And as our book says up here in pink, the chemical bonds within the molecule, intra meaning within, are called intramolecular forces. Whereas the attractive forces that exist between the molecules, or between ions and molecules, are called intermolecular forces. And I'm going to take you to a graphic to make sure that that makes sense. So here we've got two HCl molecules, and because hydrogen and chlorine are both nonmetals, or their difference in electronegativity is less than 1.7, it's a covalent bond. It's a polar covalent bond, though, because the difference in electronegativity is greater than 0.3. And these two atoms being different means the molecule is asymmetrical. So it's a polar covalent bond that exists within the molecule. But between those molecules, due to reasons we'll learn about in this lecture, there's a relatively strong attractive force called an intermolecular force. But it's significantly weaker. The attractive force between the molecules, the intermolecular force, is significantly weaker than the covalent bond within the molecule. And that's going to be true of all intermolecular forces. Even the strongest ones, hydrogen bonding, are going to be weaker than any covalent bonds within the molecule. Which is why when substances melt and boil, it is the intermolecular forces that are overcome between the molecules, the weakest forces that are overcome, as opposed to the covalent bonding within the molecule. And that's what our book reminds us of as well in green, which is that intermolecular forces are dependent on the attractions between the molecules. And we should know that attractive forces that are accounted for by charged particles, we'll learn that intermolecular forces are due to charges, are due to how close together those charges are. The closer together that charges are, the stronger the attractive or repulsive forces. And the greater those charges are, the stronger those attractive or repulsive forces. And that's going to be true about intermolecular forces. The closer together that molecules get, the stronger those attractive forces can be. And the more charged or more polar, we will learn, those molecules are, the stronger those forces will be. And that's another visitation of Coulomb's law. So we're going to go to this slide real quick before we go back to our book. And this slide shows us the 6 types of, and I'll say in quotes, intermolecular forces that we want to be familiar with and want to be able to compare the relative strengths of. The first of those and the strongest of those are ion-ion forces, or what we know to be called ionic bonding. Technically, those are not intermolecular forces, but because they aren't forces between molecules. They're forces between ions. But if we put them in this conversation of intermolecular forces, they are the strongest. The smaller the ions, by the way, and the more charged those ions are, the stronger the ion-ion forces and the stronger the ionic bonds. Next strongest are ion dipole forces. These are forces between ions and polar molecules, which we'll talk more about in our book in a bit. They're going to be weaker than ion-ion forces, because polar molecules are typically bigger than our ions and they're less charged, creating weaker attractive forces. Third is hydrogen bonding, which is very poorly named because it actually isn't a covalent bond, but is a type of intermolecular force. So when you hear hydrogen bonding, please don't think of it as an actual bond, but rather an intermolecular force. And those are between polar molecules that have something special about them. Dipole-dipole forces are between two polar molecules that don't have this special thing about them. That's reserved for hydrogen bonding. They're weaker than hydrogen bonding. Dion-induced dipole forces are between polar and nonpolar molecules. And then the weakest force, although they can be quite strong, depending on some things going on, are what are called induced dipole forces, also called London dispersion forces, or just dispersion forces, and not so commonly anymore, but still commonly used, van der Waals forces. We will tend to use London dispersion or dispersion, but they're also called, again, induced dipole, or van der Waals, and these are between two or more non-polar molecules. So we're going to go straight to the third strongest type of intermolecular force, dipole-dipole forces, which are attractions between polar molecules. I want to remind everybody once again, polar molecules are molecules that have polar bonds and are asymmetrical. Well, polar molecules, we know, are polar because they have one side of the molecule that's slightly positive and one side that is slightly negative. What will happen when two or more polar molecules are near each other is the positive side of one polar molecule will orient itself nearest to the negative side of another polar molecule. And in this case, we can see two HCl molecules doing that. The negative chloride side of one HCl will orient itself close to the positive hydrogen side of another molecule, creating an attractive force between the negative part of the first molecule and the positive part of the second molecule. It's called a dipole-dipole force. Again, it exists between two polar molecules or between the negative side of one polar molecule and the positive side of another. In blue, it tells us that the more polar those molecules are, or the more charged they are, and we know this because of Coulomb's law, the stronger the dipole-dipole forces will be. There's other factors that influence dipole-dipole forces that we'll talk about later. For now, know that the more polar a molecule is, the stronger the dipole-dipole forces are. And by the way, molecules will be more polar either if their bonds are particularly polar and or if they're particularly asymmetrical. That's what makes molecules more polar. Dipole-dipole forces, third strongest type of force behind ion-ion and ion-dipole. You may have noticed I misspoke a moment ago. I said that dipole-dipole forces were the third strongest type behind ion-ion and ion-dipole. Hydrogen bonding actually takes the third slot. Dipole-dipole are the fourth slot, so sorry about that. Anyways, moving on to hydrogen bonding, which again is a poor name for intermolecular forces because it's not a covalent bond, it's an intermolecular force. Hydrogen bonding is a special type of dipole-dipole force. It's a particularly strong type of dipole-dipole force that exists between two polar molecules that each have hydrogen in them bonded to either nitrogen or oxygen or fluorine. Again, hydrogen bonding is an intermolecular force that exists between polar molecules that each have a hydrogen in them bonded either to a nitrogen or an oxygen or a fluorine. What these are just really polar molecules that can get close together. And because they're polar and can get close together, that significantly strengthens the attractive force between those molecules. They're particularly polar molecules, those with H bonded to N, O, or F, because the difference in electronegativity between H and N, or H and O, or H and F is particularly high, creating a very polar bond, usually on the outside of the molecule. What this means is the hydrogen atom, which has always got a higher electronegativity than N or O or F, will be particularly positive. So there'll be this very highly positively charged end of the molecule that also is due to an H atom that is really small, meaning another molecule that is polar and has a large negative side to it can be quite attracted to that very positive and quite small hydrogen atom. And that's what our book says here in green, is that the partially positive hydrogen in one molecule will be attracted to the lone electron pair of the partially negative atom of another molecule. And that attractive force, as you've heard me say a couple times, will be particularly strong, not only because of the extremely polar bond, but also because those H atoms are so small and the molecules can get particularly close together. So here's a few examples of hydrogen bonding that exists between various molecules. The most common example in nature certainly is the hydrogen bonding that exists between water molecules. There's an H bonded to an O in water molecules. Therefore, there will be a strong attractive force between the H in one water molecule and the lone pair on the O in the other molecule. but just think of it as between the H in one water molecule and the O in the other. Here it is between two HF molecules. Again, here's an H bonded to either an N or an O or an F, and it's an F in this case. So the H in one molecule is attracted to the F in the other. The lone pair, but think of it as the F. Ammonia is a real common molecule that experiences hydrogen bonding. The H in one molecule, because it's bonded to an N, will be attracted to the N in the other molecule that's also bonded to an H. Hydrogen bonding can exist between non-like molecules also, if they both have H's bonded to N, O, or F's. So here's hydrogen bonding between HF and water, between HF and NH3, and then between water and NH3. So again, if in both molecules there's an H bonded to an N or an O or an F, that will result in the particularly strong type of dipole-dipole force called hydrogen bonding. Once again, poorly named. So we've talked about hydrogen bonding that exists between polar molecules that have H's bonded to N, O, and F's. Dipole-dipole that exists between just regular polar molecules. Now we're going to jump down here to this second to last row, which is dipole-induced dipole intermolecular forces, which exist between polar molecules and nonpolar molecules. And because our book doesn't include dipole-induced dipole forces in this section, we'll go back to a slide to take a look at it. So dipole-induced dipole forces again exist between polar molecules and nonpolar molecules. It turns out that nonpolar molecules can have dipoles induced in them. We'll talk about how and why in a moment. I want to remind you, though, that molecules are nonpolar if the covalent bonds are nonpolar or the bonds are polar, but the molecule is symmetrical. So one might wonder why or how a polar molecule with a positive N and a negative N could be attracted to a nonpolar molecule, a molecule that's overall neutral, because only actually opposites attract. Well, the reason why is that the polar molecule can induce a dipole in the nonpolar molecule. Take a look down here. Here's water, a quite polar molecule, with the negative side of water, the O side of water, oriented toward the nonpolar molecule. Could be flipped around, but it's not. What this means is that the negatively charged side of water is near to the electron cloud of the nonpolar molecule that right now is evenly distributed. Well, we know that like charges repel. The negatively charged side of this water molecule will repel the electrons on this side, this left side of the nonpolar molecule, and will push them away or toward the right side of the molecule. What that will do is unevenly distribute the electrons temporarily in the nonpolar molecule, inducing a dipole. That nonpolar molecule, because it's near to water, becomes polar temporarily. It has an induced dipole. And as long as the water molecule stays near to the nonpolar molecule's dipole will remain induced, and therefore the negative end of the water will be attracted to the positive end of the nonpolar, although right now polar molecule. That is a dipole, induced dipole force that exists between a polar molecule that induces a dipole in a nonpolar molecule by shifting its electron cloud to one side. If water happened to have been oriented the other way, the positive side of water were closer to the electron cloud, opposites attract, the positive end of water would pull the electrons in the nonpolar molecule toward it, and the dipole that it is being induced in the nonpolar molecule would be opposite. The positive end would be on the right and the negative end would be on the left. These are fairly strong forces because as long as, again, water is near the nonpolar molecule, that induced dipole is fairly permanent. They are not as strong, though, as dipole-dipole forces because those induced dipoles truly aren't permanent, and they're never as strong as would be a permanent and always permanent dipole in a polar molecule. This is something you'll hear me say a couple more times in this lecture. It's really key. It explains a lot about nature, which is that induced dipoles, these temporary dipoles that come from electron clouds being unevenly distributed for a short period of time, increase in strength when a molecule is more massive. When a molecule is more massive, it has more electrons. The electron cloud is bigger. There's more electrons that, at any one moment in time, might be shifted to one side of the molecule. It creates a larger opportunity for an uneven distribution of electrons. More massive molecules with more electrons typically have stronger induced dipoles. What that means is that their intermolecular forces are going to be stronger. more massive, nonpolar molecules experience stronger induced dipoles, and as a result have stronger intermolecular forces, which again, you'll hear me say again, and is commonly used to explain some of the phenomena we see in nature and in this class. All right, now we're going to look at this bottom row, the weakest type of intermolecular force, although these can be very strong, which are called London dispersion or just dispersion forces, also referred to as induced dipole or van der Waals. We're going to call them London dispersion or dispersion in here typically. Well, if you wondered a bit ago what would cause a polar molecule to be attracted to a nonpolar molecule, you must really wonder what would cause two nonpolar molecules to be attracted to each other at all. Well, it's for a similar reason that polar molecules can be attracted to nonpolar, plus one extra little bit. All right, so let's take a look at this diagram down here with the purple images. Notice there's two molecules, one on the left, one on the right. They're both nonpolar because their electron clouds are drawn symmetrically. These are nonpolar molecules that have neither a positive end nor a negative end. The left-hand nonpolar molecule, despite that its electrons are on average evenly distributed, might at any moment in time, because remember, electrons are zipping all over the atom, we never quite know where they are, might at any one moment in time be more so on one side of the molecule than the other. They might temporarily be unevenly distributed. And this molecule right here is drawn in such a way that its electrons are more so shifted to the left. That means the left side of the molecule is very temporarily slightly negative, and the right side is very temporarily slightly positive. There's a temporary dipole, or what is sometimes referred to as a momentary dipole. It's very short-lived, it's fairly weak, but it exists. So imagine the left-hand nonpolar molecule being polar right now, because it is. Well, we know polar molecules can induce dipoles in nonpolar molecules. So this originally nonpolar molecule, which due to a random uneven distribution of electrons is polar, will now make another nonpolar molecule near to it, this right-hand nonpolar molecule, polar by shifting its electrons. If the left-hand molecule has its electrons shifted slightly to the left, meaning the right side of it is slightly positive, that'll pull the electrons in the left-hand molecule toward the left, creating a dipole, and now the two oppositely charged ends of these two molecules are attracted. This, though, is significantly weaker than the other kinds of forces because, number one, the nonpolar molecule has to randomly become polar, and that doesn't happen to all molecules at once. And then another nonpolar molecule needs to come by and be close enough to it for a dipole to be induced. But this creates kind of a domino effect. Once there's a random dipole in the first molecule, which induces a dipole in the second one, that will induce a dipole in the third, which will induce a dipole in the fourth, and they all reinforce each other. As nonpolar molecules become slightly polar, they make each other more and more polar, which makes them more polar in return. And if you want to pause the video for a moment and read what I've highlighted here, this says what I just said, hopefully or possibly a bit better. Realize, though, that this can also happen in polar molecules. Although polar molecules are always polar, a polar molecule at any one moment in time might be even more polar because its electrons happen to be shifted even more so to one side, which can then induce in another nearby polar molecule a slightly stronger dipole. So induced dipole, or London dispersion forces exist in all molecules, polar and nonpolar. Now, they are the only type of intermolecular force that exists between two nonpolar molecules, but in polar molecules, you'll have dipole-dipole forces and London dispersion forces. And in molecules that experience hydrogen bonding, a special type of dipole-dipole force, they will also experience London dispersion forces. Keep that in mind because, as you heard already, the more massive a molecule, the stronger its London dispersion forces. In fact, really massive nonpolar molecules can have quite strong London dispersion forces. In fact, two fairly massive polar molecules, which experience dipole-dipole forces, might actually experience stronger London dispersion forces because they're so massive than the dipole-dipole force they experience from their polarity. So, just something to think about. And we'll come back to that as we answer some questions in a bit. So we've talked about these bottom 4 types of intermolecular forces. We're now going to talk briefly about the second row, ion dipole, knowing we already know about ionic bonding, and then do a few practice multiple choice XAP questions to test your knowledge. This will be a short section. Again, this is on ion dipole forces, and we're on page 394 of the ebook. And what it says here in orange is the attraction that exists between an ion and a polar molecule. A polar molecule which has a dipole is called an ion dipole force. These are stronger than dipole-dipole forces because not only are ions more charged than polar molecules, and remember, the greater the charge, the greater the attractive force, they're also typically smaller, so they get closer together and they're more charged. It is ion dipole forces that account for why it is that many ionic substances dissolve in water. Those ion dipole forces are strong enough to overcome the ion-ion attractions that exist in the ionic solid to account for those ions spreading out and solvating in water. Notice we've got sodium chloride here that appears to be dissociated or ionized by water. Chloride, being the negative ion, will be surrounded by water molecules, but with the H ends, the positive ends of the water, pointed inwardly, such that the negative chloride is being attracted to the positive side of the waters. Meanwhile, the sodium ions are also surrounded by waters, but in that case, the waters are flipped the other way around with the negative side pointed inwardly to be attracted to the positive sodium ion. So this is a picture of the solvation or the ionization of sodium chloride in water with the ion dipole forces labeled in these dotted lines. The smaller the ions, the stronger the ion dipole force, so that's something you could be asked about. And the more charged the ions are, also the stronger the ion dipole force, because again, size and charge affects the strength of the attractive force. All right, so here they are again, our 6 intermolecular forces in order of decreasing relative strength. Ion-ion forces exist between 2 oppositely charged ions. It's also referred to as ionic bonding. And the more charged those ions are and the smaller those ions are, the stronger the ion-ion force or the ionic bonding. That is by far, of these 6 forces, the strongest. Behind ion-ion is ion dipole, which exists between ions and polar molecules. Their strength is based on the size of the ion, smaller or more charged ions, stronger ion dipole, and also more polar molecules or smaller polar molecules, meaning those ions and polar molecules can get closer together, stronger. Third in line is hydrogen bonding, which we know to be a special type of dipole-dipole intermolecular force, once again poorly named, between 2 molecules that each have an H bonded to an N, O, or F. This is a particularly strong type of dipole-dipole force because the difference in electronegativity between H and O, or H and N, or H and F is high, and H is small, so these molecules are charged, highly polar, and can get close together. Remember, they also experience van der Waals forces, so very big molecules with hydrogen bonding that we know experience van der Waals forces might be particularly attracted to each other because of the strong van der Waals or London dispersion component. 2 regular polar molecules experience dipole-dipole forces. The more polar they are, the more attracted they will be to each other, and because they also experience London dispersion forces, the more massive they are, the greater the van der Waals or London dispersion force accounts for the overall intermolecular forces, and the stronger they'll be held together. Then we've got then we've got dipole-induced dipole between polar and nonpolar molecules, same thing. The more polar the polar molecules, the stronger this force will be. And the more massive either the polar or nonpolar molecules are, due to the strengthening of the London dispersion force, the stronger the intermolecular forces. And then lastly, we've got induced dipole or London dispersion between 2 nonpolar molecules. And more massive nonpolar molecules we know experience greater uneven distributions of electrons, so their polarities can be greater, and that makes that force stronger as well. So there they are one more time. But rarely are we asked just to predict the type of intermolecular force between molecules or to compare one intermolecular force strength to another. Rather, we're typically asked to apply the type and strength of intermolecular force to one of several physical properties. And here are 6 that are listed. I'll go over a couple of these. For example, if molecules have stronger intermolecular forces than other molecules, they have higher melting and boiling points. Hopefully you know that to melt or boil a substance, you've got to spread those molecules out and overcome or stretch the intermolecular forces. When those intermolecular forces are stronger, it's more difficult to do so. It takes more energy. It's a higher temperature at which that occurs. Stronger intermolecular forces result in higher melting and boiling points. Heat or vaporization, like a boiling point, is how difficult it is to overcome those intermolecular forces. It's technically the amount of energy it takes. Stronger intermolecular forces result in higher heats of vaporization. Surface tension is how difficult it is to penetrate the surface of a liquid, which is a measure really of how strong the intermolecular forces are, how difficult it is to overcome those. With stronger intermolecular forces, the molecules are more attracted to each other. It is more difficult to penetrate the surface. Surface tension is higher. Vapor pressure, we'll learn about later, has the opposite trend to boiling point. Know that increased intermolecular forces result in decreased vapor pressures. We'll learn why later. And the last two we'll also talk about later. Greater intermolecular forces result in greater heats of hydration and also greater lattice energies. So that's the end of the lecture, and if you feel like you've got this down and want to sign off, you can, but I'm going to spend 3 or 4 minutes going over 5 multiple choice questions about intermolecular forces to give you a chance to test your knowledge. So here's the first question. I'll read it aloud to you. Might be hard to see. Hopefully you can see it here on your screen. Take a moment to try to come up with the answer yourself, and then I'll go over it. All right, it says solid carbon tetrachloride, CCl4, is represented by the diagram above. The attractions between the CCl4 molecules that hold the molecules together in the solid state are best identified as A, polar covalent bonds, B, nonpolar covalent bonds, C, intermolecular attractions resulting from temporary dipoles, or D, intermolecular attractions resulting from permanent dipoles. Take a moment to think about what the answer is. Come back and I'll tell you what I think. All right, the answer is C. And the reason why is these CCl4 molecules are nonpolar. Even though the carbon-chlorine bond is a polar bond, CCl4 molecules with a tetrahedral geometry, which are symmetrical, are nonpolar. These are nonpolar molecules. Therefore, the forces that hold them together are from temporary dipoles, or induced dipoles. The answer is C, intermolecular attractions from temporary dipoles. All right, question 2. At 298 Kelvin, or 25 Celsius, and 1 atmosphere, bromine, Br2, is a liquid with a high vapor pressure. And chlorine is a gas. We don't know what vapor pressure is, but know that bromine's a liquid, chlorine's a gas. The chlorine molecules have spread out from each other at the temperature at which bromines are still pretty stuck together as a liquid. Those observations provide evidence, under the given conditions, that the forces among Br2 molecules are stronger than those among Cl2 molecules. The forces among the Cl2 molecules are stronger than the CCl bond. The Br-Br bond is stronger than the Cl-Cl bond. And the Cl-Cl bond is stronger than the Br-Br bond. See what you think, come back, and I'll tell you what I think. And the answer is A. Those bromine molecules being in a liquid phase means they're held together more strongly than are the chlorine molecules. That's what's keeping them in the liquid phase at the same temperature. So the answer is A, definitely not B. C is not true. The bromine-bromine bond is actually weaker than the chlorine-chlorine bond. D is true. The chlorine-chlorine bond is stronger than the bromine-bromine bond because chlorine atoms are smaller. They're both sharing one pair of electrons, and the closer together that atoms are, the stronger the attraction. But that doesn't account for why one is a liquid and one is a gas. That just would account for why the bond is stronger. So while D is true, it does not account for the phenomena. All right, question 3. We've got butanal, pentane, and propanoic acid. You're not meant to know how to name these compounds, and if you saw this on a test, you'd say, great, those are cute names. Let's just take a look at these structures and their molar masses. Notice they all have fairly similar molar masses. Fairly similar molar masses, but their structures are different. All right, based on the information in the table above, which of the compounds has the highest boiling point and why? A, butanal, because it can form intermolecular hydrogen bonds. B, pentane, because it has the longest carbon chain. C, pentane, because it has the most CH bonds. And D, propanoic acid, because it can form intermolecular hydrogen bonds. Take a look, see what you think. Come on back. All right, the answer is D. It is not A, because butanal, although it has an H in it, does not form hydrogen bonds or hydrogen intermolecular forces. The H is not directly bonded to an N, O, or F. This is just a polar molecule that would experience dipole-dipole forces and some London dispersion forces. Pentane does have the longest carbon chain, but that isn't going to make it have a higher boiling point. In fact, it's going to be a nonpolar molecule and would have the lowest boiling point of all of these. Pentane, because it has the most CH bonds. No, that is not relevant. It is D, as we know, because this can form hydrogen bonds, the strongest type of intermolecular force, other than ion dipole, but that's not technically intermolecular because the H in this one is directly bonded to the O. So it is D. All right, question 4. The London dispersion forces are weakest for which of the following gases under the same temperature and pressure? London dispersion forces are weakest for which of these? Hydrogen, oxygen, xenon, fluorine, or nitrogen? Take a peek. Come on back. When we're comparing the relative strength of London dispersion forces, it's almost always going to be about molar or molecular mass. If we're looking for the weakest forces, we're looking for the least massive molecule. Hydrogen is the least massive molecule. It weighs 2.02. The next least massive molecule is nitrogen, which weighs 28. So hydrogen, because it's the least massive, has the fewest electrons. They're the least likely to be unevenly distributed to experience those temporary or induced dipoles. It will have, by far, the weakest London dispersion forces of these 5 molecules. Question 5, last one. Based on Coulomb's law and the information in the table above, which of the following cations is most likely to have the weakest interaction with an adjacent water molecule? So we're looking at the weakest ion dipole force. Water's a constant. Which of these ions will have the weakest attractive force with water? Their radii are given to us. Looks like lithium is the smallest, calcium is the biggest. Their charges are given to us as well. So is it lithium, sodium, calcium, or indium? Take a guess. Come on back. So remember, Coulomb's law is all about distance / size and charge. The greater the distance, or the greater the size of the molecule or the ion, and or the lower the charge, the weaker the force. So we're looking for a large ion that has a small charge. Well, the largest ion is calcium, but has a 2+ charge. The second largest, and just a tiny bit smaller than calcium, is sodium with a 1+ charge. So that small decrease in radius will not account for sodium having a stronger attractive force because it has half the charge. So sodium with a 1+ charge and a relatively large radius would have the weakest attractive force to water. Strongest attractive force would come from indium with a 3+ charge because it's only a bit smaller than calcium, but it has a charge that's 1.5 times greater. All right, folks, that is it. That's our last practice problem. That is a wrap on lecture 27. I hope you enjoyed yourselves. Good luck. Make the world a better place.